Here's a recap of today's lesson where we discussed bonding in metals, and the reason for that discussion was to explain the general properties of metals, specifically ductility, malleability, and how metals are excellent conductors of heat and electricity. Now, there are many other properties, including the ones you said in class, such as metals being shiny and lustrous, but we're going to focus on these three. Okay, so the model we first introduced is a fairly simple model known as the electron. It's all about the electrons, huh? The valence electrons. It's called the electron C model, and in class I had you consider a cylinder of copper or a wire of copper metal, could be any metal, and we take a closer look at it, and it might look like this, where you have the cations of the metal surrounded by a sea of electrons. So these cations you can think of as like maybe an island surrounded by a sea of electrons, or maybe ball bearings surrounded by a glue that holds them together. Now these aren't islands or ball bearings or glue or any, this is pure metal, but just trying to make some analogies. So one key thing about this model is that these electrons are delocalized. They're delocalized electrons. They're not located in one specific place. They're free to roam around. So that electron can end up there, can end up there, can end up there, can even leave and come back if there's a circuit. So they're free to move. And these are the valence electrons we describe as the sea of electrons. And in class I had you consider applying some amount of force into a narrow cylinder. Okay, so we're applying some force, and what you'll see is that the cations can shift. Now it's not correct to say the cations are delocalized. They're not free to move around. They're more now, but if you add enough force, because of the shield of electrons that they each have, they're protecting the cations from being too close to other cations, so they're able to shift past each other if there's enough force. And so what you'll get is, in this case, the metal being drawn out into wires, and that is the property known as ductility. So we'll see metals are ductile. Okay, and you wouldn't do this with like a salt crystal or an ionic compound. Actually, we'll compare in our next example. Example number 2, I said, imagine you have a hammer. Didn't have to be a hammer, could have been just you applying a force, bending a hanger or something. But we use this here to illustrate it, so I'll use the same thing I did in class. So you have your sea of electrons, or your electron C model. So this is a sheet of metal, and you have your ocean of electrons. And so what happens is you can change that shape. You can bend it. This is called malleability. Right, that force is acting on these cations, can shift now because they're, again, shielded by a layer of electrons. And this is known as malleability. So metals are malleable, again, because of this electron C model, this model of delocalized electrons. So let's contrast here to, just go right below. Let me copy this. So say we did the same thing to like a salt crystal, one of those, candy crystals you grow when you're a kid. Oh wow. All right, and so you have a ionic compound, like there's your Na, there's your plus, attracted, electrostatically attracted to that. Chloride, attracted to that. Cation, attracted to that. Anion, and so on. And this is a 1D, and now it's a 2D drawing, but imagine this is a three-dimensional crystal and lattice, and they're going all directions. All right, but they're really locked into place, and they don't have a sea of electrons. Now, if you apply a force, right, this guy, which is positive, is going to end up here, which is negative, so this thing is going to be positive. That thing that was positive is going to be replaced with a negative. That thing negative was replaced with a positive, and you got positives facing positives, and that's no good. Negatives facing negatives, and so this is very repulsive, and this thing breaks. You didn't need a teacher to tell you that if you hammer a salt crystal, it's not going to conform in that shape. It's going to shatter. All right, and look at our second model. Here is called the band model. Get a little bit more technical with this one. All right, so what I had you consider in class was a single magnesium atom, which you would never see in a practical sense. And this can be any metal, but magnesium is kind of the one I want to use it's the one in your textbook too. So it has electrons in the 1s, 2s, 2p, and so on. But again, we only want to visualize the valence electrons because that's where the bonding occurs. And that occurs for this atom, this single atom in the 3s orbital. You'll get 2 valence electrons. A little bit higher in energy is your 3p orbitals, like that, and they're unoccupied if this is in the ground state. Okay, so this is something we've learned a few chapters ago, and this is called atomic orbitals, or AOs, atomic orbitals. Now when you have more than one atom, let's say you have 2, which is still not a practical thing. You never have 2 atoms of a metal, but say you have 2. Each of them are going to bring their own AOs, their atomic orbitals. And so I want you to see logically that you're going to get 2 orbitals when you combine 2 orbitals. Now they can't be at the same energy because Pauli says you can't do that. All right, these electrons have to have uniqueness. These are called MOs, molecular orbitals. We're going to learn much more in depth on what they are after the break. But for now, let's just make this logical. Each of these is bringing their own AOs, so you're going to get 2 MOs. Each of them bring in one of their own 3s orbital, so it would make sense you're going to end up with 2 of them now. And they can't be exactly the same energy, so one's actually called bonding and the other one's called anti-bonding. Again, don't worry about that. I want to change the color of these electrons to gray, just so it's not like everything. All right, so wait a minute. Okay, so we can distinguish them better. So now we got 4 valence electrons, right? So we got maybe 2 of them go there, maybe 2 of them go there. All right, now we're going to have 2 sets of these P's. Each of these atoms bringing in their own set, so you're going to get something like that. This might be a good time to clarify something. These guys in here, I don't spend time drawing them because they're core electrons. Core electrons, and they are localized. Localized. All right, they're not allowed out. They're not allowed out. They can't go walk around the block. They're stuck there. They're like Harry Trumpet or Truman or the Truman Show. What's that guy's name? He's afraid of the sea. All right, so sea of electrons here. These guys, they just stay home. Right, and they're attracted to the nucleus. That's probably all I should have said. All right, let's do another one. Still not practical. When are you ever going to have 3 atoms? All right, but we have 3. All right, each of them, they have their 1s, 2s, 2p, and yeah, whatever. Now, 3 atoms bring in 3 3s orbitals. You're going to get something like that. All right, and maybe there's 6 electrons now, right? 2 from each. Maybe you get 2 there, you get 2 there, you get 2 there, you get 2 there. Something like that. All right, and then now you're 1, 2, 3 from one of those, and these are these have to separate as well. So let me get to the point, because you kind of see where I'm going with this. You never have 1, 2, or 3. Even in a 24-gram sample of magnesium, you're going to have 10 to the 23rd, 10 to the 24th number of atoms. All right, so can you imagine that many atoms? Right, 24 zeros, 23 zeros, right? These orbitals become indistinguishable. Like, there's no point in drawing lines there. It's just going to look like a continuous band, right? And it's going to be full of electrons. So this here is known as your 3s band. All right, and it's also known as your valence band. You don't have to know that vocab. It's just a concept we want you to know. It's called a 3s band. And then, same thing here. Whoa, wrong blue. Now this one's going to overlap, which is characteristic of metals and conductors. This is your 3p band. And this is known as your conduction band. Again, that's not important that you know this vocabulary. Right, so here now we can finally explain this property of metals. When you connect this, here's the main point of this model. The electrons that are in here they're your electron C. This whole, they're free to move any increment to any higher orbital above it. Any quantum amount of energy that's required to move them, they're going to move into this. They're all available, so they're just free. So if you have let's go with yeah. All right. So if you connect this thing if you apply some electromagnetic force. Okay, so you got a battery here. Let's say you got a negative terminal here, positive terminal here, right? Let's not do that. So these electrons in here have room to move. The electrons on this side is like, I don't like this. I don't like this repelling force that's acting on me. I feel like moving this way. Yeah, I'm going to push you over because there's plenty of freedom. So you get this current. Metals are generally good conductors of electricity. All right, and for a similar thing, you can say also they're good conductors of heat because one way you can transfer that is through thermal, or this electron gaining that energy and just transferring over to another one, and the next one, and the next one, and the next one. So you heat up one side of a metal, that thermal energy is going to transfer pretty easily throughout the metal. sea of electrons. Let me copy this and give you one last comparison. Go right here. And I think I'm missing this guy. Narsh. Okay. So by the way, this is known as a conductor. And let's compare that to an insulator. Such as diamond, glass, plastic, wood, right? Things that you wouldn't use to connect batteries. So what they're going to have is they're going to have a valence band that's full of electrons. But their conduction band is way separated. So this is continuous here. They often overlap where the difference between the valence and the conduction band is so minimal that the electrons are free to move from an occupied to an unoccupied higher level. Whereas here you have a significant gap. So we call that the band gap. All right, again, this vocab word is you're not going to be tested on this. It's just a concept. All right, so insulators electrically, right? You can have a positive, or you can have a same. Let's do the same setup. These electrons want to go that way, but they can't because there's nowhere to go. They're just packed in there. Like you're not going to get any flow of electrons. Now you can use a similar thing. Yeah, let's leave it there.